Probability is the possibility of an event to occur and assigning a number to it. In machine learning, it is important because in our models, they do some sort of algorithm work, some sort of calculation, and based on that, they produce a certain outcome. Now, the outcomes, they aren't random, all right? They choose to pick up the most possible, most appropriate outcome based on the whole sample set or the whole situation. So this is where probability plays a big role in machine learning. Also, when I say that probability means the calculating the likelihood and assigning a number to it, so what does this mean actually? Like, in mathematical terms, you will not say that the possibility of raining is either 0 or 1. All right, you won't say that it might rain or it might not rain. All right, you cannot just say it verbally. You have to put some numbers. Like, you can say that the possibility of raining is 0.5. All right, that's a good way of proceeding to some sort of maths. But in a math, you cannot just say it might rain, it might not rain. You have to say that, yeah, it could rain. The possibility of raining is 50%, 0.5. So yeah, that's it actually. Let's get started with probability. Let's draw a sample space. This is our sample space. Here we have different kind of points. Let's say this is a point, this is a point, this is another point. So what are these points? These are the events, and this is a sample space. It contains the events. This is let's say A1 event, this is A2 event, this is A3 events. There could be multiple more and so on. So probability tells us like what is the probability of A1. This is the main part of probability. Let's talk about a dice now, shall we? This is a dice, a fair dice. A fair dice. It has 6 sides. And it has numbers on it. One, 3. There's 2, 5. Okay. So the possible outcomes from here, from this dice, would be
I'm going to denote this with curly braces. The outcomes would be 1, 2, 3, 4, 5, and 6. None other can be happen. We cannot get a 7, we cannot get a 10, we cannot get a 0. Our range is between 1, sorry, 1 to 6. Okay? So, here the possibility, probability of A1 is equal to 1 over 6. The probability of A2 is also 1 over 6. As I said, this is a fair dice. Okay? And then probability of A3, this is also 1 over 6, and so on. Probability of the last one, A6, probability of getting 6 is also 1 over 6. So how do we say this? The language here is this part. This part is value assigning. Value assigning to an event. That's what makes it different. And here, about this part, we call it the probability of event A is these values, which is here 1 by 6. And these all are equal values. So here P has to fulfill 3 conditions. P has to abide by 3 conditions. Probability has to fulfill let's say satisfy 3 rules. First of all, for every A, for every event A, P has to be greater or equal to 0. It can be anything, but it cannot be 0. It cannot be negative. What is a negative probability? What is a 0 probability? Right? It does not just make any sense. And for the second rule, it is probability of every I mean to say entire probability of the entire sample set or set of events probability of S is going to be 1. And For the third one, it is if we have a1, a2, an up to an, if we have many, when we have many, events, when we have many events, and they are disjoint. Oops. And they are disjoint. In that case, sum of probability of all these events a1, a2, a3, a4, a5, a6 is going to be the individual summation of probability of a1 plus probability of a2 plus up to probability of a6. Probability has to satisfy these three conditions. Now, what is disjoint? Disjoint is basically mutually exclusive. It means if an event already occurred, another one cannot occur. When we roll up a dice, if we get 1, we cannot get 6. If we get 2, we cannot get 3. If we get 3, what is the possibility of getting a 5? Is it possible? No. These events, these are known as disjoint event. They appear only by themselves. They appear single. They don't have a mutual connection with another. They are mutually exclusive. A dice cannot show two results together. If I would like to draw a diagram here. This is event 1. This is event 2. And this is where they intersect. This middle part right here, this cannot occur. This is what I meant by disjoint events. So, if they are disjoint, the sum of probability of all these events, they will be the sum of all the events individually. And let's say probability of a1 plus a2 plus a3 is equal to individual probability of p of a1 plus p of a2 plus p of a3, which is 1 by 6 plus 1 by 6 plus 1 by 6, which is 1 over 2. Okay, so yeah, they can't overlap. If they can't overlap, this is the rule, this is the formula from which we can bring out the sum of all the events. Moving to the next one, we have disjoint events. Let's talk about the disjoint event now. Sorry, joint probability. I was talking too much about disjoint probability, disjoint events, so that just stuck in my brain. Okay, joint probability. Okay, what is joint probability? Uh, Here, okay, let's say probability of x and y. Okay, x and y, not y, not x and y. We can also write this in like this way. Probability of x with this weird mathematical notation. We can also write this like this way. Probability of x and y. How do we say it? We say it like probability of event x and y. That's how we say it. Now, let me show you. Let's talk about. Let's go through this with an example. 52 deck of cards. In a deck of cards, we have black. Is it visible? We have black, and then we have red. In black, we have our spade, our clubs. In red, we have diamonds and heart. All of them has 13 cards in themselves. They all contain 13 cards. The cards are ace, 2, 3, 4, 5, and then 10, joker, queen, and king. All of them contains 13 cards. I'm not going to write them again here. I'm not going to rewrite, but let's just copy this one over here. Okay. Looks good. Now we are going to draw a card. Okay. If we draw a random card here, drawing a random card, the probability of it being black would be, if we are talking about black, we are just considering this portion over here, only this black side, not this red side. So black has 26 and the total card is 52. So this would be 1 over 2, half. That makes sense, right? And If we want to know the probability of getting a 4, we draw a card, and what are the chances of it being 4? So we have 4 over here, we have 4 over here, we have 4 over here, we have 4 over here somewhere, and then we have a 4 over here too. We have 4 fours. Okay, so this would be 4 over 52, which is 1 by 13. Okay, nice. But where does the joint probability come in? Where is this? What is this? Okay, so probability of black, we know. Probability of 4, yeah, that's also pretty, like the probability of 1 over 13, yeah. But what if I tell you that what is the probability of 4 and black? Okay, what is the probability of 4 and a black? So we will go over here, like this here, this portion. In, like, we have two black cards, two 4 blacks over here, this and this. We are not thinking about this red right now, we are only thinking about this black over here. So this would be 2 over 52, which is 1 over 26. So joint means basically, joint probability is basically the probability of things together. That's it. Okay. Now I'm going to show you conditional probability. Oh, this is such a nice color. Conditional probability. So we have some event of x and a vertical line, something like this. Probability of x, vertical line, and y. So this line over here, this is called given. And we say this, the probability of event x given event y. This is important, given. Okay, so what does it mean? It means that this y over here, it has already happened, it has already occurred. Given that, what is the probability of this event x to occur? Let's get back to the deck of cards over here. Let's remove these things. Hmm. Let's remove this also. Okay, so let's write probability of, what is the probability of getting a heart given that it's black. Like, we have already taken a black card. When we say black, we are only thinking about this part over here. We are only considering this part here. So, what is the probability of getting a heart given black? So, black has already happened. We took a card, and this turns out to be black. I'm using red color, but let's just say, okay. So, is there any hearts in your blacks? No. So, the probability is 0. I mean, 0 over 26. Yes, but it's still 0, right? Let's remove this. Let me show you another, like some more examples so that you can be clear about this. Probability of heart. Now let's say probability of heart given red. We have already taken out a red card. It has occurred, it has happened. Now what is the probability of it being the card being heart? So now we are only considering this part now, this part right here. So heart, we have 13 hertz here, so it would be 13 over 26. But probability of heart given black, it was 0. I hope you can, like, this example, by looking at this example, I hope you are able to grasp the idea. And now the probability of, just a minute, the probability of 4 given black, a black card happened, we took a card, and that happened to be black. Now what is the probability? Okay, we have 4 fours here, right? This is a 4, this is a 4, another 4, another 4, but we'll be talking about 2 fours here already, because I mean, we are going to talk about 2 cards here because black has happened already. So are you going to consider this red fours? No, we don't need them. Black happened, red did not happen, black happened. We are only focusing here. So this would be 2 over 26, which is 1 over 13. Okay, now from here we can make it to a formula. Let me show you. This is very interesting and this will come in handy later. Let's move this over here. And about the formula, the formula would be probability of 4 given black is divided by probability of black. Isn't it what just happened? The probability of 4 given black and then probability of black. The probability of black is 26. So this is the formula. Now from this formula we're going to move further. Probability of x given y is equal to probability of x given y divided by probability of y. This is our formula. And here's an important concept, by the way. These are known as this this concept is known as independency. It's basically, are they related or not? So x and y are they related? I will not tell you this. Comment down below your answer. Find it out yourself, figure it out yourself, and then let us know what you think about this independency concept. I'm going to show you some more other concepts of probability. Let's say it's time for another sample set. And there are segments here. Let's say this is C1. These are chunks C1, C2, and here we have C3. And this is an area A. We want to know the probability of A. Only this part. We are only interested in these parts, given that we have a sample space and there are chunks C1, C2, C3. So this is where the concept of sum rule has developed. Sum rule, this is known as sum rule. The sum rule probability of A is summation of all the chunks over here. It's probability of A and C1. A and C, like this is, if we say A C1, we are indicating these chunks over here only. It should have been yellow, not green. Yes, this specific chunks only we are talking about. We are focusing, we are interested only in this chunk. This is basically just summing up the chunks, we are basically summing up the chunks. And there are more in this. There are more to come in this formula. We are not done already. We're done. We are not done yet. We have more to see. So, this is okay. First of all, let me write this. This is basically C1 plus probability of A to C2 plus probability of A3 and C3. Okay. Now, the law of total probability. What is the law of total probability and why it's related in this probability of A? Law of total probability. Probability of probability of x given y is equal to probability of xy and probability of, okay, am I mistaking here? No, probability of y. Okay, from here we are going to develop another formula, which is, oops, okay, now let's multiply p of y in both of left hand and right hand, p of y and p of y, and then we are going to rewrite this and we will get p of x given y into p of y is equal to p of x y. And now we are going to plug it in, like the where it is p of here, we're going to plug this here, we're going to rewrite, and it would be probability of A is equal to summation of C1, and now we will write probability of A given C1 into probability of C1. It is basically sum over all those chunks, in the sample space. Okay, this is known as the law of total probability. Now, I'm going to visualize it. I'm going to show you, don't worry. Where is our sample space? Okay, here. So, So when I say probability of A given C1, we are talking about this chunk over here. Okay, you're interested in this chunk over here. A, this is part of A, of course this is part of A, given it's under C1. Okay, and when I say that probability of C1, this is basically this part over here, this part over here, including this part also, this little part also, and this whole part here, this part also, this total part over this sample space, this sample space, okay, over this sample space. If we say P of A2, P of okay, this is P of A1, and if we say P of A2 given C2, then we'll be talking about these chunks over here, this chunk over here, and if we say probability of C2, that would be only this chunk. And I'm sure you can see this. Do I have only this? Don't I have any more other colors? Okay, let's go with this one, green, a dark shade of green. But when I say probability of C2, we are interested in this part only, this little part over this whole sample space. And when I say P of C3, we are talking about, we are indicating this part over here, this little chunk. And when it's, oh, I'm sorry, when it's P of A3 given C3, then it's this chunk over here. But if we say P probability of C3, then it's this chunk. Oh my god, this is so satisfying. This chunk over this chunk here, this over this total sample space. I hope you got a good idea about the sum rule of probability, the law of total probability. So yeah, this is the formula. Let me remove this one. So this is the main formula known as law of total probability. Now let's enough of all these concepts. Let's solve some math problems so that we can understand this concept clearly. Okay, so now we'll solve a problem that is probability of me doing my homework. Yeah, I don't know how to do homework, but I have to do it. Okay, so enough talking. I have some informations here. Uh, I have okay. The informations I have is the place where I live in. Let's say I live in New York, and the probability of raining here in a day is 15% on an average day. And I have some more informations, which is if it rains, if it rains, my probability of doing homework is 95% because it's raining. I will not go outside. I'll stay inside in my room and I'll end up completing my homework. But if it does not rain, if it's a sunny day, my probability of doing completing my homework would be 30% because it's raining. I mean, it's not raining. It's sunny outside. I'll not stay in my home. I'll go outside. So these are my informations, these three pieces of information. And now I'll calculate probability of me doing my homework. Probability of HW is going to be probability of HW given it rains into probability of only rain plus probability of HW given it's sunny into probability of sun. We have the informations here, which is this is 95%, this is 15%, this is 30%, and what about this here? This is basically probability of 1 minus probability of rain. Sometimes we don't have the exact information in our hand, but we are given another type of indirect information from which we can get our hands on the exact information we want. In that case, we have probability of sun, but probability of rain, we have this one, but we need probability of sun. Okay, probability of a sunny day, which we obtained by minusing one, reducing, subtracting the probability from 1. Now, can you say why it's 1? Why not any other number? Can you recall where it is? Can you recall the 3 conditions I said where it is, by the way? Yes, the probability of the entire sample set of events is going to be 1. So yeah, this is the reason. This is the reason we are subtracting the probability of rain from 1. Okay, which is 85%. Now let's plug them in. It would be 0.95 into 0.15 plus 0.3 into 0.85 which is 0.39 or 39 point something, okay, close to 75%, or we just can say 40%. So whether it rains or not, if it's a sunny day or not, if I stay in home or not, my probability of doing homework is 40%. So yeah, I mean, would you have guessed it from these three numbers over here, these three informations here? But now you know. Not only you know, you are actually able to work on them and getting something meaningful. Isn't it great? Now moving to the next one, Bayes theorem. One of the most important concept. That's why I'm writing it in red. Bayes. I'm sorry. You will see Bayes rule in many places, but these are the same things. So Bayes theorem. I'm going to write out some formulas here, and then I'm going to give you insights on them. Probability of A given B is equal to probability of A given B divided by probability of B. Now, from here, we can rewrite this as probability of B and A into probability of B. B and A, we just interchanged the terms here, and we can do that actually. Anyways, so probability of B cancels out, and we are left with this two pieces of information here, like probability of A given B is equal to probability of B given A, which is not very helpful. Helpful in what, by the way? I'm going to show you that. Now let's remove this. But if I say that, if I rewrite this as probability of B given A into probability of A, suddenly it's very powerful. It becomes very powerful. How? Well, from here we can write probability of A given B is equal to probability of B given A into probability of A divided by probability of B. It is honestly very powerful formula. I'll tell you now why it is very powerful. Let's rewrite this. Yes, and again I'm rewriting this. Probability of A given B is equal to probability of A into probability of B given A divided by probability of B. So, what is important? Like, what is here to learn? What's so important? Important part is this little thing over here. It's called prior. It's called prior. This over here, probability of B. This is called marginal. This one over here, this is the likelihood. And this over here, this is our posterior. Posterior. Which basically means the updated probability after probability of some event after probability of A. Okay, I'm writing this. The probability of A after some new events B. Now, what does this mean? Basically, in machine learning, in machine learning, the values are constantly updating. They are constantly changed. Okay. In machine learning, we constantly update the prior, and get new distribution. New distributions every time we see a new event. That's how probability is tied with machine learning. We constantly update whenever we get a new event. Whenever we get something new, we calculate this, we we calculate the likelihood, and then we get the marginal, then we make our prior, then we do our posterior. So yeah, that's why, I mean, this is why Bayes theorem is important. And um let's do a math on it right now so that I can make it more clear to you. So let's do it with COVID testing. COVID test or any kind of diagnosis, basically. I'm talking about COVID here because that's what came to my mind when I said like applying Bayes formula into some real life work. Bayes theorem is Bayes theorem is strongly connected with the medical fields actually. In the medical application of machine learning, Bayes theorem is Bayes theorem is being applied more in there. So, anyways, when you have a disease, when you have a disease, either you get tested positive or negative. You test positive or you test negative, right? So, let's say you have actual COVID. Actual COVID. But, yeah, you have actual COVID and you got tested positive for it, which makes sense. But what if you have COVID? You are infected with COVID, but in your test report, the test says negative. You don't have COVID. The test says you don't have COVID, but you have COVID actually. It happens. It's not like it does not happen. The rate is very low, but it happens. You cannot deny it. And on the other hand, you don't have COVID, but still you can test positive for it. Your test might come out positive that you have COVID or you don't have COVID. So, what I'm trying to say is this thing over here, like the test being negative when you have actually positive, when you have actually COVID, this phenomenon, this is called as false negative. And this thing over here, this is false positive. This is called as false positive. At any given point, let me put on some numbers first, then we'll do the math. The test negative does not have negative. Let's say this is 98%. Yeah, we don't get COVID that much nowadays. And for test positive you have 2%. And let's say this is 95% because our medical equipments are very developed right now, but still it can happen. Let's say this is 5% and this is 10% and this is 90%. So now what? At any given point, suppose okay. Suppose you have COVID, what's the actual possibility probability that you have COVID? And the only info you have is you got a positive test result. There are no symptoms, no connection, contact with another COVID person whatsoever. The only piece of information have a positive test result. So, how do you solve this? I'm going to write it over here. Probability of COVID given that your test came positive. Now, this is probability of test being positive given that you have COVID into probability of COVID divided by probability of test being positive. So here something to notice is we have this here, we know this value, but about this one we don't know this. This is where the law of total probability comes in handy. We don't know straight up the probability of positive tests, okay, but we know something that is called the law of total probability. And what we're going to do now, we're just simply going to apply that formula and get our results. So let's just write the values we know for now, which is 0.95 into 0.02. But for this part, this is probability of test. Probability of test being positive with the help of the law of total probability. It is probability of positives given COVID into probability of COVID plus, I'm sorry, plus probability of positives given that no COVID into probability of no COVID, which is, we know the values, 0.95 into 0.02 plus 0.1 into 0.98, which is 0.19 plus 0.098. So we got our values. Let's plug it here. This is So the so if you have tested positive and you don't know if you actually have COVID, the probability is 66%. So in Bayes' theorem, we have applied the law of total probability. And okay, I just want to tell you another thing, that in machine learning we have this table here that's called confusion matrix. The table looks like this. It contains four values. They are true positive, true negative, false positive, and false negative. So this confusion matrix, they actually give you a summary of your ML model. So the thing is, you don't want your model to have a lot of false negative, false positive. Okay, you don't want that, because let me write this first. False positive over false negative. Because just tell me, you don't have COVID, but you got tested positive for COVID anyways. What's the worst thing could happen? Nothing. You have nothing to lose. Maybe you will be put on some medication. Maybe you will be told to maintain distance from your family members, from your pets, from your friends. Okay? But nothing, like, all just this, okay? Nothing else. You have nothing to lose. But imagine you have COVID. You have COVID, but you got tested negative. You have a false negative, which is a false negative. Okay, you have COVID, but you got tested negative. This is a false negative. And if you have false negative, what will you do? You will be like, okay, I don't have COVID. I can I can be around with other people's. Um, I mean, this causes health risk. If you have an elderly grandma or a sibling, you will end up infected them as well. Okay, you have a lot of things to lose here. uh, Remember, I said that Bayes theorem is Bayes theorem is actually um, widely actually being used widely in the medical application, like the ML medical part, I mean, in that field. Because of this thing, the false negative and false positive is alarming. You don't want your model to make a lot of false positive. You don't want that. Okay, you want to reduce this as much as possible. And about false negative, you can work on this too, but it's not that deadly. Like, yeah, it's good, it's not doing any harm. I mean, it's doing harm, yeah, but not deadly like this false positive. Imagine, you have you have another type of what can I say, you have, let's say, HIV. Okay, but you got tested negative for this, false negative. So in that case, what will you do? What will you do? First of all, you will continue doing what you were doing, and then from your blood, from your cough, and other factors, there are more factors, you will infect other people's too. Okay, other people's, which is bad. You don't want this. Okay, then let's say for pets, if we talk about pets, uh, rabies. Rabies is a deadly disease. Then corona. I mean, you get the idea. Okay, you don't want your model to make a lot of false negative. You don't want that. Your job is to reduce it as much as possible. Okay, as much as possible, less than one. That's it. So yeah, this is how probabilities are tied with machine learning. Is important, and before getting into machine learning, you should know the statistics, probabilities, calculus, and many other factors, many other machine learnings, and yeah, linear algebra also. It's important. So that's it for today. Thank you so much. Goodbye.